So we are going to chapter 8, and chapter 8 is all going to be about right triangles, which is probably one of my favorite chapters to teach, but this information is a little harder than most chapters. So we're going to spend a lot of time, like each day is going to be one section, and it's all going to be about right triangles. So before we get into the right triangles for today, there's a term that you need to know, and it's called geometric mean. And so the mean that you guys know is either being mean to somebody, or you might know like the mean of two numbers is the average. But this is a different type of mean. It's called the geometric mean. So I want to point out what a geometric mean is. And what a geometric mean is, it's a number in a proportion where the bottom of the left, which is the denominator, and the top of the right, which is the numerator, if those match, then that's what your geometric mean is called. That is a geometric mean. Now, this says find the geometric mean between 1 and 4. So I put my 1 and 4 here and here. And what happens is there's some number that matches each other that makes this true. So now this one's an easy one you can get because most kids know that 1 over 2 is the same as 2 over 4. So that is the definition of a geometric mean, is the same number in the proportion, bottom left, top right, that makes it true. So this geometric mean is 2. So that's one you could do without knowing how to solve it. You just look and say, well, what number makes it work? Oh, 2 makes it work. All right, now we're going to skip number 2. You're going to come back to that at the end. And I'm going to try 3 and 4 with you. Okay, so now I've got to think of what number is the geometric mean between 9 and 8, or 8 and 9. So I'm going to make x be the geometric mean again. That's the number in the bottom left and the top right. By the way, these are called the means position, if you've ever heard that before. And then 8 and 9 are going into the extremes position, which you don't have to know that for this year, but these are called extremes and these are called means. All right, so now you could sit here for hours and hours and not be able to figure out what it is because it's not as easy as this one to come up with. So here's how you solve it if you can't solve it by guessing. You're going to cross multiply. So we're going to get x squared equals 9 times 8 is 72. And then you're going to square root both sides. And here's where your algebra is going to come in, because we are going to want to try to simplify 72, unless it tells us to round to the nearest tenth. So I'm going to practice simplifying. So I'm going to think of the highest perfect square that I can think of that goes into 72. And it's got to go in with no remainders. So if you think of your perfect square list, that being like 1, 4, 9, 16, 25, all the way up, 36 is going to be the highest on the list that actually goes in evenly. So I'm going to make 72 36 times 2, and then the square root of 36 is going to be 6. That's going to come out, and 2 is going to stay in. So you guys did an algebra review, and this was one of the topics on there. So I would love for you to try to simplify this into 6 squared root of 2, and we'll just keep practicing that, but that's how you simplify the radical. So that is the geometric mean, which is why you couldn't guess it, because who would have ever thought it was 6 radical 2? Nobody would know that. All right, so you can also do geometric mean with fractions. This looks a little daunting, but it's not so bad. So you're going to set up a proportion. You're going to put x in the denominator of the first and the numerator of the second. That has to match. And then we're going to put 1/3 in the top and 2/3 in the bottom. Those are your extremes position. And now I don't have any idea what that is, so I'm going to cross multiply to solve. So x times x is x squared. And then 1/3 times 2/3. Well, 1/3 times 2/3 is 2/9 if I go across the top and the bottom. Now I'm going to square root both sides. And when you square root a fraction, you're actually going to split that square root into the top and to the bottom. So now I look, and the square root of 2 is not a perfect square, and it can't be simplified. And the square root of 9 is, and that becomes 3. And as long as the denominator doesn't have a perfect, or has a square root in it, then we are good. We don't have to worry about rationalizing or doing anything like that. So that is the geometric mean between 1/3 and 2/3. Okay, so you will go back and do number 2. So we're going to take this concept and use it on the back page in just a second. So kind of put it in your pocket for a second for what geometric mean is, and we'll come back to that. Okay, down at the bottom, I'm going to show you something that we're going to introduce as 2 kids and a mom, all right? And we're skipping over chapter 7, so this is a little odd, but in middle school, you guys talked about similar triangles, and similar triangles are kind of like in the same family, but they're not twins. So if you have siblings, you and your siblings are similar to each other, or you and your cousins. So when you guys think about similarity, think about things that share the same features, but they're not the same exact size. They're the same shape, but one's bigger than the other. All right, so keep that in mind for this. So this theorem talks about the big mom. So we're going to call her Big Mom. And then it's going to talk about the little kids. So I'm going to highlight the kids in black. So if you notice, you have a great big triangle in red, and then you have these two little triangles that I highlighted in black, and that's going to create 3 triangles. So what happens is the Big Mom is similar to her 2 kids. So here's one kid, and here's the second kid, and the mom is going to be similar to the 2 kids that are inside of her picture of that triangle. So when I say that, most kids are like, okay, so just think that the mom, the great big triangle, and the 2 little triangles are all similar to each other. They share the same features, and what that means is their parts or their pieces are going to be what's called proportional to each other. All right, so down here, I'm going to kind of show you how this works. We are going to start by drawing out the Big Mom triangle, and what I want you to do is I want you to draw Mom in a way where her right angle is on the left, her short side is up and down, and her long side is horizontal. So make this the short, the long, and the hypotenuse of the Big Mom. All right, now let's put her vertices in. So her right angle on the Big Mom is M, her shortest side is KM, and her longest side is ML. So now we've oriented Mom to be sitting this way. All right, so now I'm going to take one of the kids. So I'm going to pick this kid, and I'm going to draw that kid oriented the same way as I did Mom. So I'm going to put his right angle down in the bottom left, his short side here. So this would be the short side, this will be the longer side, and this will be the hypotenuse. Okay, now let's go get the vertices. So in this little kid right here, P is the right angle. If you look, PM is shorter than PL, so I'm going to put M up here because that's my short side. And then PL is my long side, so I'm going to sit L there. So all I've done is taken one and just flipped it around to line it up the same as Mom. Okay, now I'm going to take the other child, which is triangle 2, and I'm going to sit it the same way. Short side up left, bottom on the bottom will be the long, and then I'm going to make the hypotenuse across from the right angle. Okay, now we're going to list the angles of number 2, the other kid. So P again is the right angle. The short side is K, so this is going to be K. And then the long side is P to M, so this is going to be M. Now, when we learned similarity in Chapter 7, there's a similarity symbol that is a wave, and you may have learned that in middle school. All it means is that the triangles are similar to each other. So we're going to name the triangles that are similar to each other in the correct order. So you can pick any way to name the mom. So I'm just going to go triangle KML. That's my choice. You can pick whatever you want for that. Now for the rest of them, you've got to make sure that you line up the order of the triangle in the order that matches Mom. And I'm going to use a little wave to show that they're similar to each other. They're not identical, but they're similar. So if I go KML, my next one is going to be triangle MPL. And then my other one is going to be triangle KPM. Now all the orders will match up, and you can match up the pieces based on the way the triangles are sitting. So when it says write a similarity statement identifying the 3 similar right triangles in the figure, this is the Big Mom, and then these are her 2 kids, and they're all similar to each other. All right? So I'm going to leave this one blank because you're going to try it in a second to line them up the same way. And we're going to go to the theorems that are the major part of what we're going to learn today, which kind of takes those 2 things and puts them together. All right, these theorems are very complex. If you read them, it would make your head spin because it doesn't make any sense when you read them unless you know what you're doing. So I'm going to kind of walk you through these and what they say, and then we're going to look through some examples. So I want you to know that there are 2 different ones. This one is called an altitude theorem. Well, I call it the altitude theorem. And this one is called a leg theorem. Okay, now I need to go back because I want to show you something that I forgot to show you on the page before. So let me go back to this. This, when you guys are doing the similar little kids and the mom, I forgot to tell you that we've got a vocabulary word we're going to need for this section. This is an altitude. And so I want to review an altitude. It starts at a vertex and it makes a right angle with an opposite side. So if you notice in these pictures that we're working with, they all have altitudes. And so keep that in mind. That's what an altitude is, and you're going to need to know that for the back page. Okay, so let me go back to the back page then. So this is on page 46. So the very first thing I want you to notice is I'm calling this one an altitude theorem, and that's because I have an altitude. Now, one thing that you have to use these theorems is you have to have a right triangle with an altitude. So it's kind of like I think of a right triangle with an attitude. I've never really met a right triangle with an attitude, but it's a right triangle with an altitude, and that has to be present in the picture for this theorem to even work. So keep that in mind. All right, so what's going to happen is I'm going to call this theorem the heartbeat. And this theorem is going to be called the heartbeat because if you remember what a heartbeat looks like on like a monitor, then you would be able to fill out this theorem. So that's going to help us in just a second. All right, the gist of this theorem says this. If the big mom and the little kids are similar to each other, then their body parts will match up proportionally. They're going to match up in ways that have a fraction equal to a fraction. All right, so if you guys look at this proportion that they gave us, they're saying x over h equals h over y. So if you look, the small side of this kid over the long side of this kid is going to match up to the small side of this kid over the long side of this kid. And that's going to match up because they're similar. So we're going to call it a heartbeat because watch as I trace this, okay? If I trace it with a marker, I'm going to go x over h equals h over y. If you think about what those heartbeats look like, if you've ever seen like a heartbeat on an EKG, that's the same idea. So if you trace x is to h as h is to y, that is going to be the proportion that works, which is why we call it the heartbeat. All right, now, as far as what geometric mean means, if you guys look at this proportion, do you see how the h's match? So would it make sense for me to say h is the geometric mean between x and y, based on what we did in the front? So let me say it again. H is the geometric mean between x and y. And x and y are the two pieces of the big hypotenuse. All right, so down here, I'm going to write this out in words as a theorem, and then we're going to practice it. So it says, the measure of an altitude drawn from the vertex of the right angle to the hypotenuse is the geometric mean between the measures of the two segments of the hypotenuse. Okay, so let me go back up and say this. The h is the altitude. It is the geometric mean between the two pieces of the hypotenuse. Or you can think of it like a heartbeat if you want to. Okay, so let's go down and try one of those before I show you the second theorem, so you don't get too much information at once. Okay, go to this picture and I want you to circle who the altitude is. The altitude is the segment that goes from the right angle to the hypotenuse, right? So x is the altitude. That is going to be your geometric mean because that's what the theorem says. So we're going to put x in the bottom left and the top right of our proportion. Now, the theorem also said that it was the geometric mean between the two segments of the hypotenuse. So the other two pieces that match up with x are the two pieces of the big hypotenuse, which are 4 and 9. That is how you do it according to the theorem. Now, if you want to do the heartbeat, watch how you do the heartbeat. 4 is to x as x is to 9. See how I have that in there? So over, up, down, over. And all it's doing is it's just matching up the pieces of the triangle that go together and making a proportion. Okay, now cross multiply. So x squared equals 36. Square root both sides. X equals 6. So now we have what x is based on that proportion. All right, so let's try another one. Let's go over, we're going to come back and do y and z in just a second. So let's go over to number 6, and I want you guys to locate the altitude. Go ahead and circle the number that's on the altitude. Now this time it's a number and not a variable, but it doesn't matter. It's still going to work the same way. So I'm going to take the altitude and I'm going to put it in the geometric mean position. So bottom left and top right. And it doesn't matter that this was a variable and this is a number, because what's on the altitude has to be the geometric mean. Okay, now you take the other pieces of the hypotenuse and you put those in the other positions. So x and 4x. Now, the other way to do it is the heartbeat. So watch the heartbeat. Okay, this is an upside down heartbeat, but you're going to go x is to 16 as 16 is to 4x. So that's a heartbeat, over, down, up, over. So x is to 16 as 16 is to 4x. Okay, now we're going to cross multiply. So this becomes 4x squared when you take an x times 4x equals 256. You're going to divide by 4. And you're going to get x squared equals 256 divided by 4 will be 64. And then you'll square root and get x equals 8. So if you have something on the altitude, you will use the heartbeat process, or you can use the way that we worded the theorem to find a missing variable in there. Okay? All right, so now I'm going to go up and teach you the second theorem, which is very similar to the first, but this one has to do with a leg instead of an altitude. So I want you to think about the great big right triangle that we have. This is a leg, this is a leg, this is the hypotenuse. So this theorem that I'm getting ready to show you has to do with the two legs. All right? We call this the boomerang theorem because you can use a boomerang. The way that a boomerang works, you can remember that, and that might help you set it up. All right, so all I want you to imagine is that the two little kids are similar to the mom. So if you look at how these letters are lined up, this is the hypotenuse of the big mom triangle over the short side of mom, and this is the hypotenuse of one of the small triangles over the short side of the small triangle. So all you need to remember is they're just matching these up based on the fact that they're similar to each other. Okay, so let me show you kind of how the boomerang is going to work. Okay, the boomerang is going to work like this. You are going to start in in the middle here, and you are going to loop around. So just kind of watch how I'm looping around. I'm going to go x over b, and then come back around and go b over c. So x over b equals b over c. That's going to be the motion of it, but let me explain why we do that. And the reason we do that is because the second theorem says that if you have a leg in a big right triangle, it's going to be the geometric mean between the entire hypotenuse and the segment of the hypotenuse that is next to the leg. Okay, for instance, I'm going to set this one up over here by myself. So let's circle one of the legs. Let's say we choose B. B is going to go on the bottom left and the top right because that is going to be your geometric mean. Instead of the altitude, it's a leg. Now, the next thing you're going to do is you're going to pick the side or the piece of the hypotenuse that is touching that leg or adjacent. So that's going to be X. And then you're going to choose for the other position the entire hypotenuse, and that's going to be C. Now watch the boomerang. X, boomerang to B, and then you throw the boomerang to C. So I don't know if you want to use the boomerang. I don't usually use it. What I do is I put the B's in the left and right positions here, and then I use the little piece touching in the hole. But some people like to think of it as you bring the boomerang back like behind your head, and then you throw it, and when you throw it, you use the whole hypotenuse. Okay, so let me set up the other one. So let's say that we're going to use A instead of B. You're going to make A the geometric mean. So put A in the bottom left and the top right. Now, who's the piece of the hypotenuse that touches A? It's Y, so we need a Y there. And then who's the entire hypotenuse again? It's still C. So let me show you the boomerang on this side. So you take the boomerang, you like cock it back behind your head, so you go Y over A, and then you throw it A over C. And that's how I set it up there. Okay? All right, so taking that, and it's going to take a little, so if you're confused, just wait, because you're going to have to do some practice before you start getting it. Okay, so taking that idea, we're going to come down here, and I'm going to draw a little line here, because I'm going to show you how to get Y and Z. Okay, so let's say we choose Y or Z. It doesn't matter. They're both legs. So let's go with Y. So circle Y. That is a leg. That is going to be your geometric mean. So I'm going to put Y on the bottom left and the top right. Okay, now, In the other positions will be the piece of the hypotenuse that's touching the leg, and then the whole entire hypotenuse, which adds to 13, by the way. Okay, so in this position, I'm going to put a 4, and then the whole hypotenuse is 13. Now, could you switch those? Yeah, it doesn't really matter where the 4 and the 13 go. But watch the boomerang. Start in the middle, swing the boomerang back behind your head, and then let her fly. And so it goes 4 over y equals y over 13, if you want to think of it like a boomerang. Okay? All right, cross multiply. So y squared equals 52. Square root 52. Think of the highest perfect square that goes into 52. It's actually 4. So this becomes 4 times 13. Bring the 4 out. You get 2 square root of 13. Okay, now we've got to do one more for z. We could do Pythagorean theorem, by the way, but we're going to set all these up with geometric mean because it's much better to practice with this one than it is. You guys will practice Pythagorean theorem eventually. Okay, so let's do z. Z is a leg. We're going to make z the geometric mean. So the only things that can be in the geometric mean position are the legs or the altitude. So I'm taking a leg and putting it there. Okay, what's the piece of the hypotenuse touching that leg? It is 9. What's the entire full hypotenuse? It is 13. Okay, the way the boomerang goes. Start in the middle. 9 over z equals z over 13. It's like you wrap the boomerang behind your head and then you throw it, if you want to think of it like that. Okay, cross multiply. Z squared equals 117. Square root both sides. 117 actually does have a perfect square, believe it or not. It's 9. Square root of 9 is 3. So it's 3 square root of 13 for z. Okay, so we're going to do one more. We're going to finish this one out, and then I'll do a separate video of some examples in the workbook page so that you guys can see a few more. All right, now in this example, we need to take this 8 and we need to plug it back into the picture because we're going to need these pieces of the hypotenuse to help us in the problem. So if this is 8, we're going to put that 8 there, and we're going to put the 8 in here and do 4 times 8, which is 32. So it's not drawn to scale, but you're going to put those in the picture because we need them. All right, these are your 2 legs. So you can choose whichever leg you want to be the geometric mean. So let's just go in alphabetical order. Let's go y. So I'm going to make y the geometric mean by putting it in the bottom left and the top right of my proportion. All right, so when you have a leg as the geometric mean, you look for the piece of the hypotenuse that's touching the leg, which is 32, and then you take the entire hypotenuse, which would be 40, and that goes in the other position. Okay, boomerang would be start in the middle, swing your arm back, 32 is to y, as y is to let her fly, 40. Okay, cross multiply. Now this is going to be a gigantic number, so we're going to leave it as the square root of 1280. If it ever says to round to the nearest tenth, then you could make it something like 35.8, but you don't need to simplify 1280 because it's so big. All right, now we're going to go to the other leg, and we're going to do the same thing, but we're going to use the other leg as the geometric mean. So z goes on the bottom left and top right, because that's your leg. It has to go in the geometric mean position. And now you take the piece of the hypotenuse touching that leg, which is 8, and the whole hypotenuse, which is 40. Boomerang would be start in the middle, swing your arm back. 8 is to z, as z is to let her fly, 40. So if you want to do it that way, you can. Cross multiply, this is going to be big as well. So z squared equals the square root of 320. That does break down into 8 square root of 5 because 64 goes in evenly. As a decimal, if it asks you for the nearest tenth, it would be 17.9. Okay, so what I'm going to do is I'm going to have you go back and fill in the ones that we didn't do and check them, and then we're going to do a separate video on your workbook to practice some of the questions in there.